Number 20. A 100-gram toy car is propelled by a compressed spring that starts it moving. The car follows the curved track in figure 7.38. Show that the final speed of the toy car is 0.687 meters per second if its initial speed is 2 meters per second and it coasts up the frictionless slope, gaining 0.18 meters in altitude. All right, so I have a picture over here, and its initial velocity is 2. Its final velocity once it gets up this hill is 0.687 meters per second, and it rises 0.18 meters in altitude. All right, so we have to confirm that this is indeed the final velocity. So what we want to do is we want to think about this problem from an energy perspective. All right, so what might be a good idea is to realize that there is conservation of energy in this problem. Why? Because it's frictionless, all right? So there's total conservation of energy, all right? So whatever is kinetic initially may be converted or taken away by potential or whatever the case is. So the idea is to start off with the this formula, that the initial energy should equal the final energy, okay? So if we think about this, what are the energies initially in the problem? Well, there's going to be both. There can be potentially both potential gravitational energy and kinetic energy. So why don't we write that? So kinetic energy initially plus the potential energy, all right, initially, should equal then the kinetic energy in the final state plus the potential energy of the final state. All right? So let's expand on these pieces. All right, so let's just detail the formulas. Basically, they tell us what the formulas are over here on the right-hand side, right? So let's just detail them now, right? So this would be 1/2 times the mass multiplied by the initial velocity squared plus the mass times gravity times the initial height, right, will equal 1/2 times the mass times then the final velocity, right, squared, plus the mass times gravity times the final height, okay? Now, realize that every term has mass, right? So we could factor out an m from every term, and guess what happens? They all cancel. So let's just cancel them right off the bat so we don't have to work with more than we need. All right. So now now let's start plugging in some values if we know them, okay? So the first term here is 1/2 times the initial velocity squared. So what is the initial velocity? Well, it was 2. Okay, now notice I'm not really concerned about x or y coordinates. I just want to know what the velocity of the vehicle is overall. Okay, so that's one of the benefits of taking this energy approach. It might be a little easier, all right? So 2.00, that's squared. Plus then the gravitational acceleration, right, of 9.80 multiplied by then the initial height. But what is the initial height of this? Well, it's 0, right? It's on the ground. So this whole term actually cancels, right? So let me not even bother writing it, all right? So this whole term cancels, right, because the h is 0. So now that should equal then 1/2 times the final velocity. Now they gave us the final velocity, but why don't we just assume we don't know it because we're trying to since we're trying to confirm that this is the case, right? So let's just assume we don't know it. Let's see what the calculations work out to be. Then plus the gravitational constant, well, not the gravitational constant, the force due to gravity of 9.80 times then the final height. So the final height of this object here, it reached a height of 0.18 meters. 0.18 meters. So guess what our job to do is here? Calculate VF, okay? So throw this into the calculator. So it's really, right, it works out to 4/2, so this is just 2. Okay, equals then 1/2 VF squared, okay? Plus then this value, right? So 9.8 times 0.18. So it turns out to be 1.76. So plus 1.76. So subtract this 1.76 on over. Right, so then we get 2 minus that value. So 0.24. 0.24 will equal then 1/2, right? VF squared. Divide out the half on both sides. Okay, so I don't have a lot of room here, so just take 0.24 divided by 0.5. and we double it essentially, right? So then it works out to be 0.48 will equal the final velocity squared. And then all we have to simply do is take the square root of both sides, and let's hope it works out. So square root of 0.48 works out to 0.693, right? 693, and that is meters per second. So now you compare it to the value of 0.687. So we're slightly off. It's probably because of the rounding. All right, so when I probably rounded this, it probably came out just slightly different. So instead of rounding, let me actually do the, just do the exact calculation just to double check for you guys. So 9.8 times 0.18, and then we'll take 2, subtract that answer, divide that by 0.5, and then square root it. Yeah, so if you do the exact, if you don't round it all here, you'll get literally exactly 0.687. Okay, so there's no problem in terms of the math. It's just that I rounded here a little bit, but the whole process is the same. Okay, so they do match. I'll say that maybe, let me write this in here. Instead of writing equals, what I'll do is I'll write, approximate. All right, so it's approximately that, but it does work out exactly correct. Guys, thanks so much for tuning in. Please remember to subscribe, and look forward to helping you with the next question. Take care.